In an earlier presentation, we talked a little bit about what light is. Now I'd like to actually make light do something. Specifically, I'd like to interact it with matter, with materials, and see what this tells us about light, its nature, and specifically its energy. Now, if you think about it, if I shine a beam of light on an object, a piece of matter, there's only really three things that could happen. Either it's going to go straight through, as though the material's not even there, it might bounce off, or maybe some of it gets absorbed as it goes through, so less comes out the other side. These three different processes have three different names. If it bounces off, you call this a reflection. If it goes straight through, you call this transmission. And if it gets absorbed, you call this absorption. Now, these three things happen in different ways. The reflection might be simply a hard bounce. The light ray strikes the surface and bounces off. The actual interaction is a little more complicated, but we don't need to worry about it. But you could think of it as a sort of an electromagnetic catch and release. Transmission means, frankly, there's little or no interaction. Either the light went straight through and totally ignored the fact that there was any material there, or if it noticed, it didn't notice enough to have any significant interaction with it. For our purposes here, the more interesting interaction is the absorption. The light, at least in part, got caught by the material. Now remember our first important fact number one from the previous presentation. Light is just another form of energy. It behaves a little differently than some other forms of energy, as you'll see in a minute, but it is just another form of energy. So in fact, if my light was absorbed by the material, the energy of the light must have been absorbed by the material. So ultimately, this leads me to important fact number two about light. Absorbed light interacts with the matter, and because it has energy that must be disposed of, its energy must correspond to a difference between two states of the material. If this is the energy of the light, this gap, there must be a system state and a second system state, sometimes called ground state and excited state, that correspond to this energy difference. Because remember, conservation of energy, energy cannot be created or destroyed, so it must go somewhere. Now it turns out that different wavelengths of light, or radiation, interact with different parts of the molecule. Infrared radiation, this is radiation that's longer than 700 nanometers in wavelength, or lower in energy than visible light. Visible light goes from 400 to 700 nanometers. So longer wavelength, lower energy. This actually interacts with the bonds and changes the vibration of the bonds. We'll talk more about that maybe later in the course. Microwave radiation is in fact how your microwave oven works. This reacts with wavelengths of radiation even longer than infrared, and this interacts with the rotation of bonds. Visible or ultraviolet, so visible light from 400 to 700 nanometers, or ultraviolet slightly shorter than 400 nanometers, which means higher in energy than visible light, actually interacts with the electrons within the molecules. One of the simplest ways to look at it, even though it's not 100% accurate, is what's known as the Bohr model. In the Bohr model, it's a planetary model where the nucleus, which contains the protons and neutrons, is orbited by rings of electrons. And so absorbing visible or ultraviolet light corresponds to moving an electron from a lower energy state to a higher energy state. Now, if you absorb a lot of energy, so much that there's no more orbitals for the electron to go into, the electron would actually leave the atom. This is actually called the photoelectric effect. Einstein, in fact, won the Nobel Prize for his explanation of the photoelectric effect. Let me ask you sort of a silly physics question. If I hit your rubber body, just so it bounces, with a 1,000-pound truck going 50 miles per hour and you land 1 mile away, what happens if I hit you consecutively with two 500-pound trucks, each of which is going 50 miles per hour? Do you land more than a mile away, less than a mile away, or still a mile away? Turns out, if you're perfectly elastic, right, you should land the same distance away in both cases because the momentum transfer is the same. Same total weight of truck going the same velocity. Okay, that's the world we live in. Now let me ask you what would seem like a similar question. You're an electron. I hit you with a 50-pound mallet and you move up 2 orbitals. If I hit you consecutively with two 25-pound mallets, do you go up less than 2 orbitals, more than 2 orbitals, or 2 orbitals? Now it seems like, of course, if the electron gets hit with a mallet in the same way that a rubber U got hit with a truck, it shouldn't make any difference. You should end up in the same place. In fact, that's not true. Because the issue is that you have to have a landing place. So if this is the electron I'm starting with, right, if a 25-pound mallet gets me to the next orbital, and the second 25-pound mallet gets me up 2 orbitals, well then I can take a 50-pound mallet and a 25-pound mallet and get there. But if they're not evenly spaced, right, if it's 10 pounds to the first orbital and 40 pounds to the second, 2 25s won't get me there. Because when I hit it with the first 25-pound mallet, there's no place for it to land. This is what's referred to scientifically as quantization. And the easiest way to think of quantization is if you think a little bit about numbers. If you look at all numbers, the set of all numbers is continuous. What that means is there's always another number in between any two numbers. So if you take the number 1 and 2, there's a whole lot of numbers in between. 1.5, 1.6, 1.7. If you take 1.5 and 1.6, there's a whole lot of numbers in between. 1.5001, 1.5002, 1.5003, etc. There are no two numbers, no matter how close they are, that doesn't have another number in between. All you got to do is add one more decimal position. Okay, this is very different than integers. Integers are not continuous. What's the integer between 1 and 2? Answer, there isn't one, right? Integers have gaps in between where there are no other integers. So this is what's known as a discrete set of numbers. Chemically, discrete gets translated as quantized, and electron energy levels are discrete. There are energy levels that are separated by nothing. You can't actually put an electron in between two allowed energy levels. So as a result, materials are quantized. They're not continuous. Since the energy absorption relates to the electron energy, what this also means is that my interactions of light with matter are also discrete or quantized. The light field itself is actually quantized. Light comes in little packets of energy called photons. And the amount of energy in a photon is related to its color. And so if you're a 600 nanometer orange photon, you have a well-defined amount of energy, and you can't be hotter or colder than any other 600 nanometer photon. Now this is very different than, again, the way our normal world seems. Consider if I wanted to take a trip from New York to California. Can I do it by walking? And the answer is yes. If I take roughly 7 million steps, I'm there. 7 million little tiny baby steps, not that I take little baby steps, but 7 million little baby steps will get me a long distance, because every step I take gets me to a different position, and each position is closer to my destination. That's, again, a continuous journey. If the world were quantized the same way that electrons are quantized, if I wanted to go from New York to California, and there's no energy states in between, no electron orbitals in between, then if I want to go from New York to California, I have to do it in one big step. So if you consider the fact that the electron levels are quantized, and that a beam of light is made up of photons, each of which has a defined energy, it creates an interaction that's a little different than you might anticipate. In our everyday experience, a 1,000-watt light bulb is much hotter than a 25-watt light bulb. But this is not because the photons in the light bulb have more energy. It's because there's more photons. Right? Each photon has a well-defined amount of energy that's related to its color. If you've got more energy of the same color, it's because you have more photons. Now you might say, okay, that's all interesting, or you might not. Right? But what does it have to do with matter and electrons? Well, it's a question of the interaction. If I have to be in an electron energy orbital, if I'm an electron, and I'm going to shine light on the object, since the energy between the electron orbitals is well defined, and the energy of the photon is well defined, they have to match or there's no interaction. So suppose I need 10 to the minus 18 joules of energy to knock an electron off of a material. This is called the work function of a material. If you see photoelectric effect, we'll explain it in gory detail. The smallest amount of energy that will cause an electron to be emitted is the work function. So let's suppose I have a material that has a work function of 10 to the minus 18 joules of energy. Where am I going to get this energy? Well, if light and electrons were continuous, the same way the world around us is continuous, well, I could get the energy from a 10 to the minus 18 joule light bulb. I could get 10 light waves, each of which is 10 to the minus 19 joules, and shine them all on there, and I have enough energy. I could have a single light wave with 10 to the minus 18 joules of energy. Or I could even take a 100-watt light bulb, which is 100 joules per second, which is way more energy than I need, and I should be able to knock the electron off. But in fact, because electrons and light are quantized, the only way to actually get there is with a single light wave that has 10 to the minus 18 joules of energy or more. And the reason, again, goes back to my Bohr model. Right? Energy is simply not additive in the way that something like heat appears to be. It comes prepackaged in single waves called photons, where the energy of each photon is related to its frequency. And it's the photons that interact with the electrons. And so the energy of the photon, which is given by the Planck relationship, where E is energy, H is Planck's constant, which is a physical constant of the universe, at least the part of the universe we've experimented with, 6.626 times 10 to the minus 34 joule seconds. and nu, the frequency of the light, which of course, since the speed of light is lambda times nu, could also be written in terms of the wavelength of light, c over lambda, where c is the speed of light. How much energy does a 600 nanometer orange photon possess? Again, because of the Planck relationship, turns out every 600 nanometer orange photon has the same amount of energy as every other 600 nanometer orange photon. And E equals hc over lambda. Again, c is the speed of light in vacuum, 3.00 times 10 to the 8th meters per second. 600 nanometers, don't forget a nano is 10 to the minus 9. So 600 nanometers is 600 times 10 to the minus 9 meters. This is a nanometer. Right? And I multiply that by Planck's constant. It turns out that every 600 nanometer photon has 3.3 times 10 to the minus 19 joules. Right? Again, light is quantized, but it will also add if I have more photons. So if I take 4 600 nanometer photons, the total amount of energy in that beam of light is simply 4 times the energy of each photon. So 3.3 times 10 to the minus 19 joules per photon, I suppose if I want to be rigorous about the units, right, times 4 photons, gives me a total of 1.3 times 10 to the minus 18 joules. Right? Again, if I go back to my work function of 1 times 10 to the minus 18 joules, this total amount of energy is more than the work function. So if the world, at least the world of molecules and photons, was continuous, that should be enough to knock the electron off. In fact, remember, our world of electrons and photons is quantized. So even though 4 600 nanometer photons has enough energy, the photon, each individual photon itself, does not have enough energy to move the electron out of its original orbit into its next available orbit. So in fact, there's no absorption of the light. In fact, even if you take 100 watts of 600 nanometer photons, which is 360 joules of energy per hour, you can sit there with your 600 nanometer 100 watt light bulb and shine it all day long and no photons come off, because the energy of the photons does not match the starting and ending electron orbital for the electron. The only photons that will get absorbed by materials are photons that have the same amount of energy as the difference in energy between two orbitals, or as you might say, no halvesies. So again, if you think in terms of the Bohr model, no matter how much energy you shine on this system, unless there's some place for your electron to land that exactly matches the energy of the photon, nothing happens. Too much energy might knock it off, right? If you're greater than the work function, it comes off, but smaller amounts of energy that don't match gaps between allowed positions for the electron cannot be absorbed, right? So if you want to, again, in this case, free up an electron and it takes 10 to the minus 18 joules of energy, you need a photon that has 10 to the minus 18 joules or more. You can't take 1,000,000 photons that have less energy and get anywhere. You could go from one allowed orbital to another, to another, to another, and maybe then you can get away with less energy. Right? But any absorbed photon has to correspond to an allowed transition between someplace the electron is starting and someplace it's ending. And only an exact match of photon energy to electron orbital difference will work. This is the implications of quantization.